Okay. So let me summarize a little bit what we did so far. So we gave an introduction to this theory of resurgence, which is a general theory to deal with perturbative divergent series in quantum theories. So then I wanted to illustrate this theory with a very interesting example, which arises in quantum topology. So the motivation for this is to actually address a semi-realistic quantum field theory, which is Chern-Simons gauge theory. But in order to introduce this theory, I followed a different route. I talked about the Jones polynomial. And from a mathematical point of view, you can think about what I explained yesterday as the following. Given any knot, the Jones polynomial defines a divergent perturbative series for it. And then you can ask all the questions that you ask naturally in the theory of resurgence about this perturbative series. And what we show is that in the case of the figure 8 knot, which is a particular simple example of knot, you get actually a surprising result, which is that the resurgent structure of this series actually sees a very classical and unexpected invariant, which is the volume of the complement of this knot. So when Jones defined his polynomial, he defined it in this sort of combinatorial way, and there is no hint that there is such a thing as the volume of the complement of the knot inside this object. So let me make some comments about it. So this is what we show. We saw that the resurgent structure of this series phi 0 knows about the hyperbolic geometry of the figure 8 knot. But we also saw, from the point of view of resurgence, we saw a very interesting structure of singularities. This is not something that you see, for example, when you study the 80 function, where you just find isolated singularities. Here we found two towers of singularities, which are spaced by 2 pi I along the imaginary directions. The real location of this tells you the information about the volume of the knot.
Marcus, are they all logarithmic singularities?
Yes. No, in this case, there are branch-count singularities. It's like generalization of branch of logarithmic. And in the note I put in my web page, you can actually see how this generalized to branch-cut. Okay? Slightly more general, but not much more general. Now, when you look at the Stokes rays of these towers of singularities, they look like a peacock who is looking at itself in the pond, and we call these patterns of singularities peacock patterns. Okay. So what happens is that you have these kind of towers of singularities in these examples, and we thought that these deserve a name. Okay. So I hope the name will stick. Now, remember that that's just the first step, just locate the singularities. Now what you have to do is go into these singularities, look at the local expansions, and see what you find there. And in principle, you should find new power series which are not the ones that you started with. And actually, in this case, you can actually do it very systematically. And the first thing you find is that all the singularities in the towers lead you to the same power series. So these singularities, in a sense, give all the same information up to a very important proviso that we'll explain later. And then the singularities on the left give you a new power series, which actually, by the way, is quite different because, for example, you see here that you have a square root of 3, which you didn't have in the original series. The original series essentially only have rational numbers up to factors of pi. And this actually is an interesting number theoretic property of this series. And then you have a tower on the right, which is essentially related to the power on the left by a change of sign. So this is a case in which resurgence program is quite complete because you can find not only the structure of singularities, but you can also deduce what are the structure of this new series. So these new series, again, are not something that was included in the original information. And then you can ask, what is all this about? What is all this information telling us? So we found that the resurgent structure knows about a geometric property of the knot that was not explicit in the definition of the Jones polynomial, and we found some new power series. So now the question is, what is all this information about? Now, let me point out that the fact that the Jones polynomial of a hyperbolic knot knows secretly about its volume was first pointed out by Rinat Kashaev from the University of Geneva in his famous volume conjecture. But he found this connection in a slightly different way. So what we have here is a slightly different approach to this problem, and this is what I like to call the resurgent version of the volume conjecture. And this resurgent version of the volume conjecture says the following, take a hyperbolic knot, take its Jones polynomial, look at all these singularities, and the prediction of this conjecture is that there will be singularities whose real part will be plus or minus the volume, hyperbolic volume of the knot divided by 2 pi, okay?
Marcus?
Yes.
Would it be related to the classical version, or?
They are related, but not logically related. I mean, this should be part, all should be part of the theory of resurgence, in the sense that what Rinat did was to find an observable whose asymptotics is controlled. The general theory of resurgence will tell you that any observable in this theory, anything that you compute in this theory will be a Borel summation of a linear combinations of all these series. So what Rinat did was to look at an observable which led to this series here. But what we found is that if you look to this other series, which is phi 0, you will find this series in the resurgent structure. So things are related in the sense that they all fit into this general pattern, but they are logically independent in the sense that proving the volume conjecture, the original version, and proving this resurgent version should involve different information, okay? But that's in a sense a kind of different way to see why these geometric properties appear in the Jones polynomial. Now, remember that the resurgent theory tells you that once you have found the singularities, you have to keep going. So we started with phi 0, we found these singularities lead me to new power series, and now you have to redo the analysis again. You have to look at these new power series and look at their singularities and keep digging new series. And then you can do that, and what you find is that these series that appear in this construction have also towers of singularities. They lead to two new towers of singularities for phi c of tau, which was the series that appear in the left tower of the phi 0. You will have two towers, one along the imaginary axis here, and the other on top of minus v over pi. And for phi g, which are, since they are related by assigned chains, you find essentially the mirror image of this. But what is interesting is that now these singularities will lead to new power series, and what you find is that essentially you close the circle. You won't generate new series. The series of phi c are phi c itself and phi g, and the series in phi g are phi c and phi g. So you finish your catalog. Your IKEA catalog of series for this model is over. You know, you only have 3 items, okay? So these 3 items is that if you start with phi 0 and you do this resurgent game, you will just get 3 new power series, phi 0, phi g, and phi c, okay? So this is an example in which you can do a complete resurgent analysis, and as I predicted in the first lecture, I think at some point you make the full list of everything that appears in the game, okay? And this is actually a very nice example of how from a power series you get new information which was actually not implicit in the original one, not explicit in the original one. Now, one thing that I think is surprising from him is this appearance of the hyperbolic volume of the knot, and if you look at the original definition of the Jones polynomial, which was purely combinatorial, there is nothing there that actually gives you a hint of why this is the case. And this is where Witten's reformulation of the Jones polynomial is extremely useful, because Witten's reformulation gives you a very natural heuristic interpretation of why this is the case. And this actually is a very subtle, a kind of very interesting and subtle analysis based on quantum field theory, which I would like to kind of present you. So now I will be slightly more precise about this Chern-Simons theory, which has appeared many times in my talk. I will be now slightly more precise. And the first thing to say is that Chern-Simons theory is a gauge theory, like the gauge theory that Martin Heide has been talking about. So the main field in this theory is a gauge connection, A, which I'm going to take to be a SUN gauge connection. And this connection is defined on a 3-manifold N, okay? Now, what makes the difference between this theory and Yang-Mills theory in 3 dimensions is the action functional for this connection. Now, if you remember, in Martin's talk, he was defining the action for this type of theories, and he used the curvature of this connection. Now, in Chern-Simons theory, you use a different functional. So you take the connection, you are in 3 dimensions, you take the differential of this connection, you get a 2 form. You can take a wedge product with A itself, so you get a 3 form, and then you get another 3 form by taking wedge A, and then you take all these 3 forms, you take the trace, and you integrate over M. And why this is so different from Jan-Mills theory? Well, the reason why it is so different is in defining this axial functional, you never appealed to a Riemannian metric. Here you only use the differential structure of the 3 manifold, you just use the wedge product and the differential. You don't need a metric in order to define this action. This is in sharp contrast to what happens in Jan-Mills theory in 3 dimensions. And this means that this theory with this axial functional will be very different from Jan-Mills theory in 3 dimensions, and will be what is called a topological quantum field theory. I cannot review all this in detail here, but what you can do definitely is, at least formally, to define the partition function of this theory as a formal path integral. So now I will exponentiate this action with a coupling constant k here, and I will take a formal definition of this, and in a sense defining this rigorously is exactly what Martin Heidegger was talking about, but we are not going to deal into the rigorous definition of this theory. We are just do something that physicists are very good at doing when they have such a path integral, which is to do perturbative expansions around it. This is what quantum field theory textbooks are about. You don't deal into the subject of defining this path integral rigorously, but you learn how to produce perturbative series, okay? Now, let me point out that this coupling constant k that I introduced here plays the role of an inverse Planck constant, and this is the 1 over tau that I was defining at some point in my previous lecture. What is very also subtle here is the following. The Jan-Mills action is gauge invariant, completely gauge invariant, but the Chern-Simons action functional is not fully gauge invariant. You make a gauge transformation which is not connected to the identity, the action will actually change by an integer multiple of 2 pi. And this is a subtlety of the theory. Actually, I will use my... So the action, the Chern-Simons action is actually multivalued. Now, if this theory is to be well defined, this means that when the action functional changes by an integer multiple of 2 pi, you will multiply this exponential by e to the 2 pi I k times an integer. And for this to be well defined, k also has to be an integer. So this is the second important subtlety of this gauge theory, is that in principle, your coupling constant k should be an integer, and in other words, the inverse of the Planck constant should be an integer. But this is, again, not a problem if what you want to do is to do perturbation theory. Now, there is an additional thing that is important in this theory, which is what are the classical solutions of the equations of motion. Now, in Jan-Mills theory, these are relatively complicated equations, but actually in Chern-Simons theory, the classical equations of motion are very simple. These are connections which are flat, for which the field strength f of A is 0. And these are much more geometric because they have a direct geometric interpretation. So these are going to be the saddle points for doing a saddle point analysis of this path integral. Remember that at some point in my lecture, I was introducing one-dimensional integrals for which you can do saddle point analysis. This is what actually physicists do in order to do perturbative expansions. Essentially, any saddle point of this action functional should be a base point for doing a perturbative expansion. And here we have learned that the base points for doing this perturbative expansion are going to be flat connections. Okay? So this is, if you want, the kind of basic classical Chern-Simons theory. And now we want to try to relate what we did to this kind of framework in quantum field theory. Now, the first object that we had was phi 0 of tau. So how do we get this series? Well, this series is going to be a saddle point expansion of this path integral of Chern-Simons theory. But what is the context in which you have to do this path integral? Remember that this theory is defined by a gauge group and a manifold M. And once you have defined the gauge group and your manifold M, this path integral is formally well defined, and you can do perturbative expansions around critical points. So in order to recover phi 0, what you have to do is to choose your gauge group to be SU2, and your 3 manifold is going to be the complement of your knot inside the 3 sphere. And it's an old result of Rosansky, Lev Rosansky, that if you do this path integral, formally this path integral of Chern-Simon's theory, around the trivial flat connection A equals 0, which is always a solution of the equations of motion, you do the path integral around this, you will get phi 0 of tau. So actually, let me point out that expanding around the trivial connection is what people usually do in Yang-Mills theory. The perturbative series that people compute in order to compare to experiments in LHC are doing in Yang-Mills theory in 4 dimensions by computing perturbative expansions around the trivial connection A0. Oops. Okay, so this gives you a path integral interpretation from phi 0. Okay, so this is what phi 0 means from the point of view of gauge series. Now, remember what I was telling you, I think, in my first lecture. The Resurgence structure of phi 0, so the structure of Borel singularities of the Borel transform of phi 0, should know about other saddle points in this game. So it might happen that there are additional saddle points in this classical theory, and the Resurgence structure of phi 0 should actually know about them. So this actually, you can even be more precise about that. You can actually locate, you can actually identify the location of these additional singularities as Chern-Simons functionals of the other connections in the game. Remember that when I was in my first lecture, I was telling you that when you do a saddle point analysis, perturbative series through their Borel transform know about the other saddle points, and the location of the saddle points are the actions evaluated at these other critical points. So the same thing should be true here. And actually, the new power series that appear when you do this Resurgence analysis should be the expansions of this theory around the new saddle points. So remember that here we found this 5G and 5C. So phi 0 is the expansion on the trivial connection. So we expect phi G and phi C to be expansions of this path integral around different saddle points of this path integral, of this Chern-Simons action. Okay? So this gives you a kind of very nice interpretation for these 3 series, but there is a very important catch, is that you just consider the original theory with S group SU2, there are no other saddle points. So what is going on here? So is this kind of breaking down? What is going on here? Well, there is a very important subtlety, which is, I think is something that is not sufficiently emphasized, is that when you do a path integral, you really have to complexify your theory. And I cannot resist noting, explaining to you that this was first noted by Valiant, Parisi, and Boros in a very different context, which was in quantum mechanics. So this is one of my favorite papers, so I just want to explain a little bit what they do, because this is very relevant in actual serious studies of resurgence. So what Valiant, Parisi, and Boros did was to study a potential in quantum mechanics, which was just the pure quartic potential. Okay? So you look at the pure quartic potential, classically what you have for a given energy is a particle which oscillates between these 2 points. And then if you try to think about other saddle points of this classical theory, that are in principle known, because the only kind of classical motion that you have here in the real plane, in real space, are actually these oscillatory motions. So they were very, very surprised that you don't seem to have room for other saddle points appearing in the theory. But then what they realize is that when you look at this potential in the complex plane, you don't have 2 turning points, because this is a quartic potential. You have actually 4 turning points, 2 on the real axis and 2 on the imaginary axis. And what is going on is that when you allow your particles to oscillate in the complex plane, they will have motions also on the imaginary axis. And there is some sort of complex version of tunneling which involves these 2 additional critical points, so these 2 additional turning points. So what they realize is that if you want to really understand the full Resurgence structure of the perturbative series that appear in quantum mechanics, you have to really complexify your theory. And even in quantum mechanics, you have to think about not only motions on the real line, but actually motions on the complex plane. So the message is that if you really want to understand these critical points that appear when you do this anisotropic transform, you have to consider your theory but complexify. Now, this means that if we really want to understand these three series, we'll have to consider Chern-Simons theory but complexify. Now, what happens? What is Chern-Simons theory in 3 dimensions complexified? Well, it was actually pointed out by Witten that if you complexify Chern-Simons theory, so instead of having the gauge group SU2, you have the gauge group SL2Z, what you have is a theory which describes gravity on the manifold. So Chern-Simons theory with complex gauge group essentially is a theory of Riemannian metrics on these three manifolds. Now, when this three manifold is the complement of a hyperbolic knot, the equations of motion for this theory are going to describe Riemannian metrics with constant curvature, and this is exactly what we are seeing. This is exactly why the hyperbolic volume of the knot is appearing. The hyperbolic volume of the knot is appearing because the complexified theory is describing Riemannian metrics on the complement of the knot. But you see, it's actually quite subtle because, of course, none of this was actually present in the original Jones polynomial, but part of this was not even present in the theory with just real compact gauge group, SU2. You have to really go to the complexified theory to see all this. And then, once you understand that you have to complexify the theory, then the Chern-Simons action of these new complexified flat connections which are going to be identified with Riemannian metrics will give you the hyperbolic volume of the knot. So this finally explains why hyperbolic volumes appear in this resurgent analysis, and it actually confirms the idea that you have to complexify your theories if you want to really understand the full structure. So you cannot just start with the real theory, you have to really go to the complex theory if you want to really understand everything that appears when you do a detailed analysis, even of perturbative series. So, in particular, phi g of t gives the asymptotic expansion of complex Chern-Simons theory around what is called the geometric connection, which I think I defined it here. The geometric connection is the complexified flat connections which corresponds to the complete Ricci flat metric with constant curvature. So as I was saying, when you complexify Chern-Simons theory, all connections will get complexified. The classical saddle point will be complex flat connection, and there is one specific complex flat connection which is called the geometric connection which corresponds to this metric. So we started with a gauge theory, and now we are describing like actually gravity on these three manifolds, not just a gauge theory. But this is very specific to this example in 3 dimensions and to Chern-Simons theory. So this actually is the expansion of complex Chern-Simons theory around this geometric connection, and phi c of t, which is the other series, corresponds just to the complex conjugate connection. So this explains why we have found the volume of the knot appearing in our game. And now there is another feature of this description which is actually also evident when you look at Chern-Simons theory, which was this structure of towers. You know, this structure of towers, which was given this kind of peacock feathers in my structure of the Stokes rays. And that's actually very easy to understand now, because remember that I told you that Chern-Simons action is only well defined up to 2 pi I. And precisely all this tower is reflecting this multivalueness of complex Chern-Simons, of complex and real Chern-Simons theory. So this is actually very specific to this theory, to this Chern-Simons theory. We don't expect, for example, this structure to appear in Yang-Mills, because precisely the multivalueness of this Chern-Simons action is what is going to lead to these towers. Okay? So let me point out that the need to complexify Chern-Simons theory in this case, I mean, this is a general prescription that comes from general studies of instantons in quantum theory, but in this precise case, you know, this was actually very much emphasized by Stavros Garoufalidis, Sergei Gukov, and by Edward Witten himself. And I'm just rephrasing some of their arguments and adding some new ones in this context. Okay, so I have like maybe 10 minutes, so let me actually finish my analysis, because as we can say, you know, in this example, you can really do this resurgent analysis in detail, and it has a lot of connections to nice physics. But remember that a resurgent structure is just not, it's not a list of singularities, it's not even a list of series. We have to know how the series relate among them, and the information on this relationship was encoded in these Stokes constants. Okay? So Stokes constants will be associated to the different singularities. Remember that in every singularity appearing here, so for example, these are the singularities of phi c. So here, you know, this is a singularity whose series, again, is phi c. So this means that there is going to be a Stokes constant relating phi c to itself. There are going to be a Stokes constant relating phi c to phi g. There are going to be a Stokes constant relating phi g to itself, phi g to phi c, etc. Remember that these were matrices which were labeled by the different type of series that they appear. And so it's very important to try to calculate them. So since we have an infinite number of singularities, we have a priori an infinite number of Stokes constants to calculate here. And the question is if you can actually calculate them. Well, one could think that since these towers are essentially trivial because every singularity gives you the same series, this Stokes constant will also be, say, trivial, will be the same ones for all the singularities. But we actually found out that this is not the case, and these Stokes constants are actually very rich invariants of the knot. Because everything that I'm using here are topological invariants of the knot. These perturbative series are topological invariants of the knot. So the Stokes constants that we find here are going to be new topological invariants of the knot. And this is actually one, if you want, additional advantage of Resurgence, is that it gives you a framework in which you can actually define potentially new invariants of the knot by using, for example, Stokes constants. So in order to give you an idea of how this goes, I'm going to label each of these series by an index sigma, and this index sigma corresponds to one of these flat connections. So in the case of the figure A knot, which has been my favorite example, the index sigma will take three values, 0, G, and C. Okay? Now, it's very easy to see that if you want to calculate this Stokes constant, you have to be careful because you have an infinite number of them, and a very powerful way to encode all this information is to consider what are called products of Stokes automorphisms. This last part of the talk is a little bit more technical, but I just want to state a result. Let me give you an idea of how this goes. Remember that Stokes automorphisms essentially encode how one power series relates to the other. And they depend on an angle theta, okay? So in our situation, we have towers of singularities. So one way to encode all the information in these towers together, in the same object, is to take products of this Stokes automorphism along all the different Stokes rays. So remember that we have two peacocks in the game. So if you look at the picture here, there are two peacocks, one peacock on the upper half plane and one peacock on the lower half plane. So we are going to take Stokes automorphisms which take into account all the feathers in the peacock up, and another product of Stokes automorphisms that takes into account all the feathers in the peacock which is in the reflection in the pond. Okay? So I'm going to define two matrices, and each of these matrices will include an infinite number of Stokes constants associated to all the possible singularities that appear here. And this turns out to be the more convenient way of encoding this information. Okay? So we actually calculated this series, these Stokes operators, and it turns out that it's very easy to see that they are square matrices labeled by sigma and sigma prime. This is just because these are operators relating one power series to the other, so there will be as many as pairs of sigma and sigma prime, and each entry on this matrix is going to be an infinite series in this parameter q twiddle, which is e to the minus 2 pi I over tau. So q twiddle is different from q. Q was the variable in the Jones polynomial, which was e to the 2 pi I tau, and this is q twiddle, which is e to the minus 2 pi I over tau. And for those of you who like modular transformations and things like that, you can see that here I'm doing a modular transformation in going from tau to minus 1 over tau. Okay? And what we found in this calculation is that, surprisingly, the series that you take in this way, after a natural normalization for this perturbative power series, have integer coefficients. And when you have an infinite number of integer coefficients, something is going on, right? I mean, you just cannot get infinite number of integer coefficients like with no reason, okay? And I will explain you in a moment how this goes, but I just want to mention that we really actually did this calculation in full detail. And just to give you, these are the power series that appear when you consider the upper feathers of the peacock, okay? So you can see that these are very nice power series in Q-twiddle with integer coefficients. And notice also that this matrix has 2 zeros there, 2 zero entries here. And this is actually interesting. This means that phi 0 needs phi g and phi c in order to have a close relation, a close structure. But phi c and phi g, you do not need phi 0. Okay? Phi 0 lives in a sense in a corner of this space, and phi c and phi g form a resurgent structure by themselves. Okay? And this seems to be generically the case. So phi 0 is a very special series, and you could actually have a theory in which you only have phi c and phi g and you never see phi 0. Okay? And this is actually the case. There is a theory which is called the theory of state integrals, which only knows about phi c and phi g, but not about phi 0. Okay, as I mentioned, these things are integer invariants, and this is for a reason. It turns out that the part of this matrix here turns out to be related to what is called an index, so a quantity which is manifestly based on integer numbers, which was defined by Dimofte, Gayotto, and Gukov. And actually, the Stokes matrices that we calculated reproduce this index, which is actually an index in a quantum field theory which counts states. So these integer numbers, as I was saying before, integers do not come without a reason. And the reason why these integers are coming out in this way is because they are counting states in a related quantum field theory. Okay? So this, in a sense, explains the integrality of the coefficients. But, and this has been actually explained using categorification, this observation of ours recently in a work to appear by Gayotto, Kahn, Moore, and Yan. And we actually have found not only these integer invariants related to Dimofte, Gayotto, Gukov, because this is just this 2 times 2 submatrix of the matrix, but there are 2 new entries which are actually completely new. They are not related to anything that we know. And this is actually related to another invariant of knots, which has been introduced recently by Gukov and Manolescu. So you see that the resurgent structure that we are finding not only has an intrinsic interest and describes completely this structure, but it actually makes contact with tons of invariants appearing in quantum topology in a totally unexpected way. I mean, everything I'm saying here are highly non-trivial conjectures. Some of them have been justified by categorification recently, but these are actually highly non-trivial facts of life. And as I said, it seems like Resurgence is giving a unified version of all these invariants together. You have the perturbative series are perturbative invariants of the knots, and then by calculating the Stokes constants, you get the integer invariants of the knots. So it's quite beautiful structure that appears in the end. Okay, so I'm now concluding. Okay, so I have talked about 2 things. I have talked about the general theory of resurgence, and I have talked about an application to knot invariance. Now, the general theory of resurgence I think is really a wonderful framework to think about quantum theory. And it's a way of thinking about quantum theory in which you don't really care too much about how path integrals are defined. You just think about formal power series and their relationships, and you try to reconstruct things out of that. I mean, this is an interesting program. I don't know how successful it's going to be. I don't know how powerful it's going to be. But it has many interesting spin-offs, and one spin-off is, for example, when you apply to the right theory, for example, Chen-Simon's theory, you learn a lot of things. You put this volume conjecture of Rinat Kashaev in a new light, you can make contact with many new invariants, and it all appears related in a very beautiful way. And I think it actually gives a better understanding of all these things, and potentially leads to new invariants. So, in a sense, you can think about these Stokes constants as new invariants in topological quantum field theories associated to perturbative series. But of course, the question you could ask is what are going to be all these structures in more complicated theories. So this is it's a more ambitious problem. So how you would apply all this framework to realistic quantum field theories. Because at least everything that I have defined, you could actually calculate it for Yang-Mills theory, for QCD, at least for quantities which have asymptotic expansions. Okay? And since this is very close to what physics is actually true, because this is how people calculate corrections in realistic quantum field theories, this mathematical framework, this theory of resurgence, might lead to important insights. And as I was saying, this might even suggest an alternative point of view on quantum theory in which you forget about the path integrals and you try to base everything on this type of structures. And in principle, you can reconstruct exact answers. And this is why you do all this work. You do all this work because you pass from asymptotic expansions to Borel-Risson perturbative series. And in principle, you have the hope that this will reconstruct exact answers. So I think this might lead to actually a very powerful point of view on quantum field theory, but there is still a lot of work to do. Okay? Thank you very much.
Thank you. Any questions? Are there any micros? Okay, let's start from Julian.
Hi, so thanks for a really wonderful set of lectures. But the last point, I just wanted to ask you on that. So what then takes the place of actually providing the original perturbative series that you need to seed your, your technology? If you say we do away with path integrals completely, where do we get from the original perturbative expansion that you need?
Well, you can think, I mean, in a sense you get path integrals, but only in the sense of being tools to produce perturbative series, which is actually what we do, actually.
Then I understand what you're saying.
Yeah. No, that's what I mean. I mean, it's like you could think about perturbative quantum theory as a set of instructions, which, by the way, you don't need path integrals to do that. You could do a Hamiltonian formulation in order to do perturbation theory, right? It's less convenient, but you could do that. So that's what I mean, in the sense that...
Yes, but you need something. You're not thinking of like also classifying all possible perturbative series that you can start off with. That still has to come from one of those structures that you mentioned.
Yes. I mean, the starting point should be given by conventional perturbation theory. That's true, yeah.
Okay, thank you. I think there was a question in the middle of the room.
I wanted to thank you for the course. It was very nice, this correspondence, but I wanted to understand what's the point of using figure-8 knot and what's going wrong when using other kind of hyperbolic knots? Yes,
okay, thank you for the question. So figure-8 knot is the simplest hyperbolic knot. So this is a case in which we can actually give very, very explicit results for everything. Now, we expect that many of the things I have said are valid for all knots, for example, for all hyperbolic knots. For example, this idea that the singularities, the phi 0 exists for any knot, including for all hyperbolic knots. So this idea that, for example, the singularities of the Borel transform of phi 0 are going to involve the volume of the knot, we expect that this is something to be general for whole hyperbolic knots. Now, when you actually do calculations, these calculations are not that simple. Calculating, for example, this power series is not that simple. So we know this power series for figure-8, we know it for the next hyperbolic knot, but doing the actual calculation for a generic hyperbolic knot is very complicated, okay? And that's why I use the figure-8 knot to kind of give you a concrete flavor of what you get. So that depends also on how you like to do math. I mean, some people like to do math in terms of general theories, and some people like to do math in terms of cute examples. So figure-8 knot is a cute example where you can test the general theory.
But then you change the quantum field theory.
No, the quantum field theory remains the same. I'm always thinking about complex Chern-Simons theory in this complexified version, and you can just change the knot, and this will give you new perturbative series in each case. In particular, once you go beyond the figure-8 knot, there will be more than 3 perturbative series. Here there are 3 perturbative series. For example, for the next hyperbolic knot, which is the 3-twist knot, which is 5-2 in the standard table of knots, for this knot, this matrix is a 5 times 5 matrix. So you see that there are more and more flat connections, there are more and more saddle points, there are more and more series, and this becomes more and more complicated. Okay? But we expect that many aspects of what we are saying are going to be general. For example, the Stokes constants should still be integer numbers, which might be harder to calculate, but they are going to be integer numbers and so on. And we have conjectures to what some of these numbers will be in general. It's just that doing explicit calculations becomes hard.
Okay, yeah, there is a question there on the left.
I wanted to ask, have you done some numerical calculations for other knots that indicate that this would still be true?
Yes, yes, absolutely. No, everything I'm saying is backed by calculations. So, for example, for the next hyperbolic knot, everything I'm saying is completely verified, and some aspects of this have been also tested for more complicated knots. For example, this resurgent version of the volume conjecture, there are evidence for this for many other knots. Okay, so everything has been backed, but there are a lot of things to do. So this is really there are still a lot of open problems for young people who want to work on them.
Okay, that's a good news.
There is a question here.
Yeah, thank you very much for the nice set of lectures. I have a bit of a far-fetching question, I think.
Yes.
So I know the Jones polynomial more from the side of representation theory of breakgroups and hacker algebras and so on. And so now you basically go first from representation of breakgroups to the Jones polynomial, and now you went from the Jones polynomial to this resurgence theory. Is there also a direct link between representations of hacker algebras, for example, to this resurgence theory, in the sense of, for example, that maybe some of this integer-valued Q tilde is maybe a coefficient of which labels the representation of hacker algebra in some sense? Did people look into this at some point?
Yeah, I think that's a very good question. My answer is that we don't know, and we don't know much. But it's true that this series, also I showed them to you in this way, they have a structure. I mean, this Q series, for example, they can be obtained by natural mathematical constructions applied to these knots. Okay, so they are not arbitrary. And for example, the fact that they are related to this index of Dymov, Gayok, and Gukov is an indication that they are more natural. But what you are pointing out is slightly different. It's a connection to representation theory and to maybe there is some module from which this Q series is some sort of is related to some sort of trace of some operator on this module and so on. And actually, people are looking at these kind of things. But this again is like an emerging area of research, but it's true that there are all these Q series and they look like they will have an interesting geometric interpretation and algebraic interpretation, but this is still very much, open at this point.
Great, yeah, it's very interesting. Thank you.
Okay. I don't know whether there are any other questions either here in the room or online. It doesn't seem to be the, well, yeah.
Hi. Sorry if I forgot something. This are node of field.
Sorry?
Are this node of field? The field. What is the substance of this node?
I don't hear you very well. Can you speak louder?
You talk about nodes.
Yes.
And are these nodes of field?
Are field.
Field.
Field. They are made of fields.
Yes.
Well, they can be described by a quantum field theory. So you can think about these nodes as some sort of defects in a quantum field theory, which is this Chern-Simons theory. Yes, that's true, yeah.
But if these are nodes of field, why they appear and why they remain? Because it's not like a rope. If a node appear, there is nothing that force two parts of the rope to join.
No, they are, no. Actually, the fields, the fact that there are fields there means that, for example, you cannot actually cross them. I mean, if you try to cross, these tubes, the fields will actually make an impact in how these knots are made. And you can, for example, not really cross one of them with the other. You cannot, for example, undo the knot because precisely of this effect of these fields. And this can be seen very clearly. You can actually calculate, how you can actually calculate very quantitatively what is the resistance of the knot to be undone violently, precisely because of the existence of this field. So you can think about these things as tubes of chromoelectric field of Chern-Simons theory, and this actually also explains why, for example, knots which are twisted and have non-trivial structure will give you a different value than knots which are not twisted. So this actually is physical. There is a physical effect of the field on why these knots are twisted.
Okay.
So in a sense, they are made of rope. There is a rope that makes these knots, but this rope is actually the Chern-Simons field. Like you see, it's very interesting what you're asking, because the beginning of knot theory, this is just an historical remark, but the first theory of knots, the reason why knots were actually classified at the end of the 19th century is because many physicists thought that atoms were made of knots of electric fields. So Lord Kelvin, for example, was a big made this big proposal that all different atoms were different knots of electric fields. And then, this was like, in a sense, the string theory of the period. And then the reason why people started classifying knots is because the different knots would correspond to different types of atoms, and this led to the first topological classification of knots. So the knot theory started as the idea that knots are actually tubes of a gauge field, which in this case was an electromagnetic field. Just an historical comment, which I think is interesting.
Okay. And are these nodes, the description of these nodes, totally independent of any space-time representations?
Of what?
Of any space-time representations?
No. You can think about these nodes as they live in the three-dimensional space-time. So they are really, they are formed by specific space-time configurations of the Chern-Simons field. Yes.
Okay.
All right. I propose to postpone further questions to maybe the next conference and the time after this talk. So let's give a very warm applause to Marcus. So the bad news is that that was the last talk of the conference, and so the Young Researchers Symposium ends here. And on behalf of the organizers, I would like to thank all the mini-course lecturers and all the contributors, all the session organizers, and actually all participants for making this event possible. So people who came here, that's great to see your faces here in the room. We also thank the online participants, and of course we thank all those people who were working on making this Young Researchers Symposium possible. So thank you very much, and I suggest one more huge applause for everybody. So thank you. So thank you. And well, that was the bad news that this conference ends, but the good news that we now have 1.5 days which are free. Unfortunately, the weather doesn't announce to be very welcoming, but still we should profit. And then on Monday morning, I hope we'll see many of you at the International Congress on Mathematical Physics. And maybe just one thing, whether you noticed, it's not here, not in this building, right? Please check the program. It's actually on the other side of the lake in the big conference center. Just check carefully. It doesn't take place here on the university campus. And well, I hope to see many of you, most of you, maybe all of you on Monday morning. Thank you.